thank you for the introduction and good afternoon, everybody. I'm gonna talk today about my research done during a part of my PhD in collaboration with Francesco Ginelli in the University of Aberdeen, and a special and very fantastic group, experimental group from Florence, made up by Francesco Marino and Giovanni Giacomelli. This is a work which is made up by two parts, which is a numerical and an experimental part. Okay, so I'm gonna show you both the results from the numerical point of view and also from the experimental point of view. I put this symbol on every slide to thank the European Union, who is providing the funding for my project. Otherwise, I couldn't have done this research and even traveling between Aberdeen and Florence. So I'm really grateful, and I support the European project. So starting from directly the state of the art, to understand what I've done, you need to first look before at the state of the art. Two main papers which came out in the previous years. The first one, made by Giovanni Giacomelli, Francesco Marino, and others, that is dealing with the properties of lasers with long delay feedback. Okay, so it's a particular bistable lasers. What is the behavior of these bistable lasers when you apply a long delayed feedback? Okay, so they study in particular coarsening properties and things that are especially connected to the complexity which is bringing the long delayed feedback. And also, you will maybe remember an experiment made by the group of Katsumasa Takeuchi, that is dealing with critical phase transition in turbulent liquid crystal. He showed with an experiment, it's a brilliant experiment, I suggest you to have a look, that this critical phase transition is belonging to the direct percolation universality class. Oops, and it disappeared. Okay, come back. So I was saying that he showed these properties of this phase transition, but there are not a lot of experiments which are showing that phase transitions occurring in one-dimensional systems. Okay, but in particular for phase transition belonging to the universality class of the direct percolation. Okay, so here comes my paper, which has been published recently. You see, it's last days of April. So if you want to have a look, it's online. The story I'm going to talk about is here, and I'm going to prepare now a longer work. So if you're interested in these things, I think you can get all the updates you will need. So first, I want to transmit you some easy concepts. I know for some of you this is trivial, but it's really important to start from this. So in hypothesis, you have a bistable system. So what does it mean, bistable? Just starting from the basics means that you have a system which is two possible stable states, okay? Just by definition. But let's suppose that your system is, can be described with a potential, okay? So we call it the potential bistable potential, just because there are two minima. We call, just take a quartic potential, okay, with two possible minima, and let's assume that one minima is higher than the other, okay? So you agree with me that if you add noise in the system, then the noise is acting in two ways. The first way is, let's suppose you are in the highest minimum, okay, and you act with some noise, okay, depending on the amplitude, but if the amplitude is great enough, you can, if you are sitting on the highest minimum, you can be pushed on the lowest, just for the effect of the noise, right? But if you are sitting on the lowest and you have noise, okay, what if your noise is a multiplicative noise or just a noise which is going to zero exactly in the lowest minimum? Means that the noise is acting everywhere in the system, but not in the lowest minimum. So some way you have a noisy system, but it's not noisy at all in the lowest the lowest minimum. So your minimum, okay, is an absorbing state. It means that once you get there, you don't go out anymore, because it's a minimum of the potential. Even if you have a delay feedback, I mean, you're in the minimum, so even the delay can't help you, and the noise is zero, so you stay there forever. And let's assume that your dynamics is made up by two contributes, okay, so your system is a bistable system, it's noisy, but also you have a delayed feedback as a mess, okay. There are a lot of things. These things together are building up non-trivial non-equilibrium transitions, okay, and we're gonna see what I mean with this. So from the experimental point of view, this is not only a model, okay, but it's an experiment running in Florence. Now, just the experiment, the concept of the experiment is really easy. Of course, the experiment is not. I'm doing the theoretical part, and so the idea is that you have a laser, okay, and the laser is in a loop, okay, it's running into a loop, and you are being pumped, okay, with this laser, which is passing through a polarizer and detector. At a certain point, the analog signal is converting into a digital signal, okay, and the digital signal, so it's an optoelectronic system, okay, just to make sure that, and the digital system, the digital signal is re-elaborated. In particular, the signal, okay, is summed up with the delayed feedback of the signal plus a noisy component, okay. I'm gonna tell you later what is this noise component, and then it comes back to the loop, okay, and just it comes, and then it's running into the loop, so it's just evolving this way. Then this is the scheme of the experiment, okay. For maybe it's not really clear what happens, but we are gonna see now. So let's assume that you are the theoretician and just you want to make a model. You want to build up a qualitative model for this system, and let's say that you want to describe the intensity of the system as a function of time, okay. And what do you do? So you have a bistable system, so the intensity of the laser is depending on the bistable potential. So the derivative of the intensity at time t is depending on the bistable potential, so it's depending on the derivative minus the derivative, sorry, of the bistable potential. Now here it's a parametric bistable potential. See, it's the parameter A. It's really important because it's the asymmetry of the bistable potential. It means that it's the different height of the two minimum, okay. And it's gonna be the most important parameter of my research. Then you add delay feedback. Now here tau is just telling you that you are taking the delayed feedback at the time t minus tau, okay. So tau is the delay, okay. So it means that you stored in your computer a signal which was tau time in the past, okay, or tau time steps in the past, as you want. So of course the feedback coefficient is positive, is a constant greater than 0, and so you just want to see the system, and you can already say, okay, I want to just in my mind thinking about two possible minimum, and in my system I want the lowest minima to be stable and absorbing. As I said before, like the noise needs to be 0 in the lowest, and in the highest I want to be active, the system. So here is, just remember, blue is the absorbed state and red is the active, okay, just for later. So you add to the equation what is missing, which is a multiplicative noise. Now the noise eta or at time t is a delta correlated noise, and the amplitude of the noise is proportional to the x. So x is again the variable which is describing the intensity of the laser. And This is a particular multiplicative noise because it's reproducing what we want. It's going, it's 0 in the lowest minimum. Okay, so in blue, okay, you don't have noise, you don't have the potential. The potential actually there is, but it's equal to 0. You don't have noise, and the feedback is 0. Okay, so once you get there, you don't get out anymore. Okay, so just to make a point about the history, state of the art of absorbing state transitions. Fortunately, Ingo introduced already before the equivalence between long delayed systems and space-time systems. So fortunately, I don't have to spend a lot of time. I was a bit worried because it was the most important part of my presentation. So I'm gonna a bit run, but I think it's clear to everybody that if you have a system which is evolving in time with a delay, okay, so a delayed feedback, of course, okay. If the delay is long enough, you can always see your system not only as a purely temporal system, so it means that, let's say you have the intensity of a laser evolving in time. The intensity of a laser is evolving in only one variable, which is time. But given the fact that you have the delay, you are not only a temporal system, you can see the system as a bidimensional system, okay? So with a time and a space. And if you want to see, like visually, you have your time with which you evolve your system. You have a signal because the equation here is just giving you a signal, okay? So it's a time series, and you take the time and say how many delays did I run my simulation. Okay, so how many delays, how many is your new variable, time variable, which is theta, is a discrete time variable, which is telling you how many delays you evolved your time, your system, sorry. So sigma in this case is how many fractions of delays did you run your system more than theta tau. So it's another variable, it's a discrete variable which is telling you exactly where you are in the system. So in this case, you see your system is not anymore a temporal system, but it's if you want to see, for example, if you want to do it numerically, you need to discretize the time. Okay, so you can see as tau sites evolving in time. Okay, and the time is given by your theta variable, and the position in the if you want the lattice, okay, is given by sigma. Okay, so there's a conjecture really important given by Janssen and Grasberger. She's saying you that let's suppose that you have a short-range interaction system with a certain dynamics, and you have a phase transition into a unique absorbing state. Then the interaction is telling you that this transition, okay, is belonging to the universality class of the direct percolation. Okay, what does it mean? It's belonging to the universality class. If you never heard about this, there is a particular, in the normalization group, belonging to a universality class means that you have the same exponents, so critical exponents of this universality class. In this case, the exponents, the three independent exponents of the DP universality class are the one, for example, let's assume that you compute the density of active states. Okay, so you have 1, 0, 1, 0, 1, 0, you sum up, this is your density, and you want to look in the critical point, what is your the behavior of this density with time, and in the critical point, this is a power law. And then for supercritical points, you have that the stationary states are scaling as a power law with the distance from the critical point. Okay, and approaching, of course, the critical point, you need to be close to the critical point. And one other exponent is the dynamical exponent, which is connecting time and space. So let's you have normally finite size effects in your simulations, even if it's really big, and the last exponent is giving you this information. So what I found, I'm gonna finish soon. What I found in my simulations is, remember the blue and white and red. So I have the three values of my control asymmetry control parameter, and you see that on the right there is the active phase, and on the left for subcritical values, okay, I found a system which is going to zero really fast. It's exponentially going to zero. In the beginning, to inverse the coexistence, okay, you say it's numerical, maybe it's not reproduced in the experiment. Okay, you're happy, and that's exactly the same in the experiment. Okay, it's really recognizing the same property of the experiment. So what I'm showing you is that there is an evidence of a critical phase transition in these systems. So what I'm gonna do is I'm gonna calculate the exponents, the critical exponents. So the first exponent, which is the decay, temporal decay, is reproducing well. You see the red one is my numerical data, and the black one is the DP class, and you see there's a really well done compatibility between the two. And the second one is the scaling of the stationary states, which is compatible again, and you hope the third one is going to be compatible, and voila, in fact this is compatible. So we find the three exponents of the universality class, and in the end, we claim that bistable systems with long delay and multiplicative noise belong to the direct percolation universality class. That is my main result of the research. These are the results of the experiment. Okay, of course, if you work with lasers, you know why they couldn't have that precision. I showed you with numerics. But the experiment is showing a very good agreement with the time decay with the universality class. So I'm done. So, and the conclusion is that, as I showed you, I am reproducing evidence for this kind of systems to belong to the DP universality class. It was really important also to bring a strong background for the experiment running in Florence. I hope I didn't get you bored, but if you I'm gonna make some publicity to the place I come from. So I'll just show you some pictures, and thank you for the attention.
Okay, thank you so much for the nice talk. Questions? Yes, Ingo.
Maybe I missed a trivial point. Yeah. What is in the experiments actually the bistable states? Are these the polarization modes of the system?
Yeah, exactly.
And how much does it depend then what you observe on the difference in gain between these two modes?
So actually, first you can reproduce the same experiment with changing not the control parameter of the symmetry, but the feedback constant. So you keep one constant and you change the feedback. But experimentally speaking, what the potential is given by the intensity of the laser, and if it's what you want to know is the asymmetry parameter, okay, is proportional to the coarsening of the laser. So some way, when you're running the experiment, you don't fix the asymmetry parameter, but you start with the lowest, and then you increase the intensity of the laser. At a certain point, you will pass from a subcritical phase to the supercritical, and that's really the big issue in the experiment, because the intensity and the properties of the lasers, of course, are fluctuating in time because of overheating. So the parameters are not constant, as you know surely. But the idea is that the asymmetry parameter is connected directly to the coarsening of the system. That's the main point.
Okay, more questions? No? Okay, thank you so much again.
Thank you.